Welcome to the course Stability Aspects of Structural Steel Design, Concepts and Applications. In this class, we will solve some problems using effective width method. Now, let's look at the problem 1. It has three different types of cross sections. The cross section of an axially loaded compression member is proposed to be selected from the three dimensions shown below. Determine the maximum axial load carrying capacity of each of these cross sections. Assume the yield strength of the material to be 320 Newton per millimeter square, Young's modulus as 200 kilonewton per millimeter square, and the Poisson's ratio is 0.3. So you look at the cross section 1, which is a box section 200 mm by 200 mm, square box section with a thickness of 2 mm. And then the inner radius is 2 mm and the outer radius is given as 4 mm at the corners. And there is another cross section where the sides are 100 mm by 100 mm and the thickness remains the same as 2 mm. And then there is a third cross section where the sides are 100 mm and 100 mm and the thickness is now 4 mm. The inner radius is given as 4 mm and the outer radius is given as 8 mm, as you can see on the picture on the rightmost side. So now let us evaluate the three cross sections and understand which one has the highest load carrying capacity. To do so, we need to identify what is known as a section classification. So the step 1 is the section classification. And to carry out the section classification, you need to find out the internal distance. Here, the internal distance is B, which is 200 minus 2 into the thickness 2 and divided by T, which is 2. So we have 196 by 2, which is equal to 98, which is the B by T ratio for the first cross section. The next cross section, we have the B by T as 100 minus 2 numbers of 2 divided by the thickness 2. We have 96 by 2, which is 48. And the B by T limit, which is the big to thickness ratio as per IS 800, is given as 42 epsilon for class 3 cross sections. So 42 epsilon is given as 42 into root of 250 by 320, and this value is 37.12. The 42 into epsilon y is 250 divided by Fy. Here Fy is equal to 320. Hence the value of 42 epsilon is 37.12. Now this 37.12 has to be compared with the B by T ratio. For the first cross section, 98 is greater than 37.12 and it is classified as slender section. And for the second cross section also, we get B by T ratio as 48, which is greater than 37.12, which is also classified as a slender cross section. Now let us calculate the effective area. For cross section A, which is 200 by 200 by 2, we have the flat width, which is 200 minus 4, which is equal to 192. Here the flat width is B, so we have to take the corner radius also. The corner radius is 4 on one side and 4 on the other side. So 200 minus 4 is equal to 182 mm. So the slenderness factor is given as lambda equal to 1.052 divided by root K into B by T into root of F max by E. Here F max is the maximum stress that is allowed. Hence, here F max is equal to 80% of the yield, which is 0.8 into 320, which is equal to 256 MPa. So when we substitute that value of F max equal to 256 MPa and Ks 4.0, because all four sides simply supported, we get a value of lambda equal to 1.81. This 1.81 is greater than lambda equal to 0.673. Hence, the reduction factor rho is given as 1 minus 0.22 divided by lambda. And this value is 0.49, which is again less than 1.0. So the effective width is B sub E is equal to rho into B, which is 0.49 into 192, and B sub E is equal to 94.08. So basically, we say that only 49% of the width is effective, and hence the effective width is 94.08. So the cross section is 4 numbers of VE into T, which is 4 into 94.08 into 2. We get a value of 752.64 millimeter square. And for the cross section B, we have 100 by 100 by 2. A flat width here is calculated as 100 minus 4 minus 4. Here the outer corner is 4 on one side and the outer corner radius is 4 on the other side. So 100 minus 4 is 92 mm. The slenderness factor is given as lambda equal to 1.052 divided by root k into b by t into root of f max by e. Here also k is taken as 4.0 because all the four sides are simply supported. And the only difference here is that the flat width is 92. So when we do so, we have a lambda of 0.87, which is greater than 0.673. So we have to use a reduction factor rho, which is equal to 1 minus 0.22 divided by lambda divided by lambda. When we run the numbers, we get 0.86, which is less than 1.0. Here, 0.86 indicate 86% of the width is effective. So rho into b equal to 0.86 into 92, which is equal to 76.12 millimeters. Now, when we do the numbers, we have 4 numbers of BE into the thickness. We have 4 into 76.12 into 2. We have 632.96 millimeters square. Now, let us look at cross-section C, which is 100 by 100 by 4. So, the inner dimension B can be calculated as 100 minus 2 numbers of 4 divided by 4. Here, the 4 represents the thickness is 4 mm. So, when we do so, we get 92 by 4, which is equal to 23. So 23 is less than 37.12, which is a non-slender cross-section. Hence, no local buckling occurs in this type of cross-section, and the entire cross-section is taken as fully effective. So we do not need to calculate the rho factor here in this cross-section C. So now let us calculate the capacity of each one of those cross-sections. So the load carrying capacity for cross-section A, which is 200 by 200 by 2, we need to add the corner radius. The corner radius is given as 2 into pi into 4 plus 2 by 2 divided by 4 into 4 numbers into 2. So we are taking the circumference of the circle, which is 2 pi r. Here r is the mean radius, the outer radius is 4, the inner radius is 2. So 4 plus 2 by 2, which is equal to 3, which is the mean radius. We are taking 1 quadrant of the full circle, which is basically 1 by 4. So we take the mean circumference divided by 4, which is giving you the 1 quadrant. And we have 4 such corners. So we multiply by 4 and then we multiply by the thickness 2. So the value is 37.7 millimeters square. So we add that to the cross-sectional area. We also know that the corners are fully effective. So 752.64 plus 37.7, cross-section area of 790 millimeters square. So for cross-section B, which is 100 by 100 by 2, we have the total cross-section area 632.96 plus 37.7, which is the corner area. The total area becomes 671 millimeters square. So the load carrying capacity for the first cross-section is 790 into 256, which is 202 kilonewton. The load carrying capacity for the second cross-section is 632.96 into 256, which is 162 kilonewton. The third one, which is the cross-section 100 by 100 by 4, we have the corner radius 2 pi into 8 plus 4 by 2. Here the outer radius is 8, inner radius is 4. So the mid radius is 8 plus 4, which is basically 12. 12 divided by 2 is equal to 6. So 2 pi into 6 divided by 4 into 4 numbers into 4, which gives you the value 150.8 millimeters square. So the area of cross section is 100 minus 2 into 4 minus 2 into 4, which is the flat area into 4 numbers, which is 1344 plus 150.8, we have 1495 millimeters square, which multiplied by 256 gives you 383 kilonewton. So what we can understand is that the first cross section is having a greater load carrying capacity 202 kilonewton compared to the second load carrying capacity. When we compare the second cross section with the third cross section has a high load carrying capacity, which is 383 kilonewton compared to 162 kilonewton. So the highest load carrying capacity is cross section C, which is 100 by 100 by 4, followed by 200 by 200 by 2, which is cross section A, and the lowest load carrying capacity is 100 by 100 by 2. Now let us look at the second problem. Here the cross section is subjected to bending. So problem 2, a 2 meter long box girder is to be tested in a laboratory under concentrated load at midspan. The cross-section of the girder is shown in the figure. Assuming that the failure of the model will be triggered by the yielding of the compression flanges, estimate the failure load of the model. Take the yield strength as 320 Newton per millimeter. Young's modulus E as 200 kilonewton per millimeter square and the Poisson's ratio as 0.3. Now let us look at the simply supported beam with a concentrated load at midspan. the distance between the support is 2 meters or 2000 mm, and the supports are having Q by 2 and Q by 2 as the reaction, and the depth of the box gird is 150 mm and the width is 300 mm, the thickness is 3 mm. Now the stress distribution due to bending is that the top is in compression, bottom is in tension, and the web is subjected to both compression as well as tension. Now in this cross section, we have the red color area that is basically under compression. The instability occurs in the elements under the compression. And let us find the effective width of each of these elements under compression. The inner radius is 3 mm, the outer radius is 6 mm, as you can see here. For the top compression flange, we have the flat width as 300 minus 6, which is the outer radius minus outer radius on both sides. We have 288 mm. And then the slenderness factor lambda is equal to 1.052 divided by root k into b by t into f max by e. K is taken as 4. The flat width is 288. The thickness is 3. F max is 80% of yield, which is 256. When we run the numbers, we get 1.81 as the slenderness. 1.81 is greater than 0.673. So there is a reduction factor that we need to be applied. And the rho is given as 1 minus 0.22 divided by lambda. So the value is 0.49, which is less than 1.0. So 49% of the width is effective. So the effective width is rho into B, which is 0.49 into 288. So the effective width is 141.12 millimeters. So the effective cross-section area is B effective into T. So 141.12 into 3, we have 423.36 millimeters square is the effective cross-section area. And we can split that into two halves, so one side as well as the other side. So we have a value of 70.56 on the left-hand side and 70.56 mm on the right-hand side. Now we need to look at the effective width in the web of the cross-section. So to do so, we need to find out the y bar. So the neutral axis location from the bottom is given by this simple strength of materials equation. As you can see here, we calculate the value here, which comes out to be y bar equal to 44.7 mm. We need to keep in mind here the corner radius is ignored and only the flat portions are considered. Hence, we need to use the flat portion in calculating the y bar. Here the width of the web element under compression is given as 144 minus 44.7, which is 99.3. So now let us find out the effective width of this compression portion in the web. So we have identified the portion that is under compression, which is 99.3, and we need to find out how much of this 99.3 is effective. So for the web under stress gradient, we have this kind of a stress plot here. So when we look at Appendix A of AISIS 116, which clearly defines the compression as well as the tension portions, as you can see here, for the elements that are under compression, the stress gradient is given as B1 and B2. And the first portion of this one that is highlighted in the red color box is what is of interest to us. So we can see that there is a portion that is B1 and we should also find out the portion that is B2, as you can see on the figure on the top. So how do we calculate B1 and B2? Now B1 and B2 can be calculated using the equations that are given on the right hand side here. To do so, we have to find out F1 and F2 because we need to find out psi because we need to find out K. So let us find out F1 and F2. So F1 is the compressive stress that is acting just below the corner radius, and it can be found out from the linear stress distribution. So F1 is equal to 256 into 144 minus 44.7 divided by 150 minus 44.7. Here we are taking the topmost edge, including the corner radius, is where 256, that is the maximum stress that can take place. So if 256 is going to take place at 150 mm, so what will happen at 144 mm? So that is the linear variation that we have found out here, and we can get the value of 241.4 MPa, that is compressive stress that is acting at 144 mm. F2 can also be found out from similar triangles here. So 256 is the maximum stress that is going to take place. So F2 equal to 256 into 44.7 minus 6 divided by 150 minus 44.7. Here also this 44.7 does not include the corner radius. So we are taking 256 that is inclusive of the corner radius. We are doing this linear variation and hence we get a value of 94.09 MPa. That is the tensile stress that is acting at the bottom. So we have got F1 and F2. So now we have to find out the psi so that we can find out the value of K. That psi is the web under stress gradient is given as modulus of F2 by F1. So we have 94.09 divided by 241.4. We have a fraction of 0.39 as the psi. Now we can use this value of psi, but before that we need to find out the aspect ratio of the cross section. The aspect ratio of the cross section is given as H0 by B0, which when it is less than or equal to 4, you have a different set of equations, and when it is greater than 4, you have a different set of equations. Here, our H0 by B0 is less than 4, because H0 equal to 150 and B0 equal to 300, which is equal to 0.5 less than 4. So here we have to use the equation K, which is the elastic stress buckling coefficient of the plate, which is equal to 4 plus 2 into 1 plus psi the whole cube plus 2 into 1 plus psi. When we substitute psi equal to 0.39, we have K equal to 12.15. So now the web depth in compression is 144 minus 44.7, which is equal to 99.3. The slenderness factor lambda is given as lambda equal to 1.052 divided by root K into D by 2 into F max by E. We have the K equal to 12.15. We have D equal to 99.3. So the lambda is given as 0.357. So 357 is less than 0.673, which means that the reduction factor is 1.0. Basically, there is no reduction that takes place in the compressive zone of the web. So we have the effective width, which is rho into D, which is 1.0 into 99.3. So B1 is given as BE divided by 3 plus psi. So 99.3 divided by 3 plus 0.39. So we have B1 equal to 29.29 millimeters. So B2 equal to BE minus B, which gives a value of 70.01 millimeters. So B1 plus B2 equal to 29.29 plus 70.01, which is equal to the total B effective, which is 99.3 in the compressive zone. So the compression portion of the web is fully effective. Now let's calculate the effective cross-section properties. So we need to calculate the value of Ixx for the entire cross-section. Here also we are ignoring the corner radius in the calculations, and we get an Ixx of 7.766 into 10 power 6 millimeter power 4. We know that the section modulus is given as Ixx divided by y top. Y top is 150 minus 44.7. So we have Z equal to 73751.19 millimeter power 3. And for a simply supported beam with concentrated load at midspan, we know that M equal to Fy into Z. So let us equate moment capacity with the maximum moment in the beam, which is Q by 2 into 1000. Okay, 1000 is the lever arm distance and Q by 2 is the reaction. So 256 into 73751.19 is equal to Q by 2 into 1000. So now we can find out the value of Q equal to 37.76 kilonewton. Thank you very much. Look forward to meeting you in the next class.